Okay. So in the last session, I was showing how to get the bound on unitary operators. So here A and B would be Hermitian generators, and we got this perturbation bound. And A is equals to A dagger, B is equals to B dagger. Okay. Today we will be looking at Trotterization, and there we will be looking at the bound of the type e to IA, e to IB minus e to IA plus B. And we will get a bound of the type of there will be some constants still involved, and I don't remember if the constants are trivial or not. So it will be scaling with the commutator of those two operators. And we derived this bound by considering the integral and then taking the derivative. So in this case, maybe I will call this 1, 2. In case number 1, we considered an ansatz. Qx was kind of interpolating between A and then I1 minus X B. Okay, so we were taking this, and then we had basically not S integral dx qx, and then it was useful to, here we had the derivative from 0 to 1, still 0 to 1. The borders are important because Q1 is e to IA and Q0 is e to IB. And the sign flip, it's just in the norm. So dx qx like this. Okay. And we will get the bound on this one. On number 2, we will consider a different ansatz where we will have e to ix a, e to ix b, and then e to I1 minus x a plus b. Okay, we can consider such a bound. And we will play the same game for both. Okay. So this integral trick here is general. Yeah. And today I want to show a couple of things. So first of all, in both cases, Qx is a unitary operator, right? Because we can view this as a composition of a unitary operator with a unitary operator, or 3 unitary operators together. Okay, so we were discussing that those exponentials of Hermitian operators are unitary. So now what does it mean to integrate those unitary operators? So let's say I have dx qx, and one question that we might ask is whether this is, for example, again a unitary operator, and the answer will be no. Okay. Because it's like a summation, not a product. So it's much better to be taking products, and under summation, U1 plus U2 is most likely not unitary anymore. And to check this, we would take U1 plus U2 dagger, U1 plus U2, and we will get twice the identity. And we will get U1 dagger U2 plus U2 dagger U1. Okay, And unless they are inverting each other, it's not unitary. Or unless this cancels itself into the identity. So unless this is minus identity, then they are not jointly unitary anymore. Okay. So this sum is not something interesting in terms of those unitaries, but it's useful for bounding things, because if we go from 0 and 1, we get exactly this difference. So how to make sense of such a sum? And one idea is d equals 1. In that case, e to I a is a complex phase. Okay, so and a is some complex number, or actually here it's the generator, so it will be a real number. Okay, so the one-dimensional case is actually already very interesting for such integrals. And what I want to show today in the first part is why this kind of stuff, why this stuff works. Okay, because we take the integral here and then change this, and something particular happens there. So the plan will be to show telescoping, and the continuous version of telescoping in some way would be stationary phase approximation. And the discrete counterpart of the stationary, so telescoping plus something called, I call it Kuzmin, but it's also called Kuzmin-Landau. If we take those two things together, we get the stationary phase approximation. And why this is important is that, as we said, for unitary operators are normal, okay? Because u dagger u is equals to u dagger is equals to identity, okay? So there exists an operator, let's call not like this, R, which is again unitary. This is like a curly U, such that R U R dagger is a matrix of the form I phi 1 all the way until I phi d, the dimension, and phi k is real. Okay, so the spectrum of unitary operators is only derivatives. The spectrum of unitary operators is only phases. So one thing that comes into mind is what happens if I have different phases and I integrate those phases or sum them up. So let's go from k equals 1 until n. Okay, and the thing that happens is that there's some sort of cancellation happening. And in the one-dimensional case, we have this qx, which is e to ix a, maybe some number a, and then ei 1 minus x b. And then we could make this into some sequence in the one-dimensional case, qk, and then we could have xk, and xk could be just delta x times k. Okay, just linearly going through, and then qk would be qk times delta x would be going to the integral dx qx at some point. Okay, so and now if we look at this, this is more or less e to ixk a minus b. That's something we can do in the abelian case when the matrix is commute, and basically we are just summing it up. So this would be a geometric sequence because we could consider e to I a minus b to power xk. And then we would be summing this up. So there are those phases involved. And what I want to show now is that if I'm considering the derivative dx qx, then this is approximately so, and let's say at x equals to y, then I could consider this to be qy plus epsilon minus qy divided by epsilon, okay? Which means that we are looking at differences of this function at different position. So if I'm integrating dx qx here dx, then this is equivalent to summing up those differences divided by epsilon. And now, just a reminder, this was going from 0 and 1, so this was q1 minus q0. Okay, and here I would take the limit of epsilon going to 0, and here I need to sum over some yk. Right? So that's Riemann sums. And this was very useful. This transition was very useful. So I thought maybe I would mention a little bit about those phases. And that will be useful later today because there is one useful trick that we would like to look at. So how to say this? If I have ak plus 1 minus ak, and then k goes from 1 until n, then this is equal to, how do we do this? an plus 1 minus a0, okay? And this is called telescoping. And the idea is that this actually looks similar and this also looks similar, okay? So for a discrete sum, if we consider a telescoping sum, this telescoping sum works this way, that it gives us those values on the edge. So we can either consider the continuous case, which is the fundamental theorem of algebra, or we consider this telescoping. This is actually not so super useful for considerations, but I just wanted to explain why those bounds are working. Because we will see still the third case, which will be useful for quantum compiling for a bound there. And we see that we can get this bound, we can get this bound, and for each of them we are using this, those integrals. And those integrals are useful because we use the fundamental theorem of algebra, but actually what happens is that here we are doing this kind of telescoping. Okay, and I wanted to mention this telescoping because in the one-dimensional case you can get quite strong bounds, and what happens is that the stationary phase approximation comes into play, and actually there is some additional dephasing going on. So I just wanted to mention this. I will show it now. One second. Just searching for the page. Okay, there it is. So we will get to Trotter-Suzuki decomposition today, but I just wanted to mention one thing. So here's the number of the archive number of the paper. And basically in this paper, I was using this for showing dephasing. And actually there is a possibility of maybe deriving stronger bounds in the non-commutative case. In the commutative case, you can consider discrete sequences, and there's a very beautiful trick how to get telescoping into the problem. Basically, you okay, I will show this trick because this is something a little bit different than what we have in our problem. But if I'm summing e to I phi over k, then I can write this as sum over k e to I phi k divided by e phi k plus full screen e phi k plus 1 minus e to I phi k, and then times e to I phi k plus 1, just removing this e to phi k plus. So basically this is what happens here. No, this is what happens here. And then in this kind of lecture note on whatever is happening here, this reshuffling in terms of telescoping happens. And basically then there are some tricks. I just wanted to mention that there are magic tricks about objects like this because it looks like this, and because this looks like this, there is something where the real part is constant, and there are additional cancellations, and it's very important. So I just wanted to say that there is a possibility of deriving additional bounds. And this is related to something known in analysis where one would derive different bounds. So this is how it looks more in the mathematics side, where they are using some funky notation, and it's much more maybe difficult to just read the paper. But at some point, maybe we want to discuss this a little bit, and just as an exercise. My point here is that this is including dephasing, and the dephasing happens if there's a monotonous sequence. To get a monotonous sequence, you can chop your function variation just into pieces, and then it's bounded in terms of gaps of that sequence. So there's some bound on the gap of the sequence, and the gap of the sequence is exactly what we were doing just before. Is basically the derivative on the edges, and that's how stationary phase approximation can also appear. I just maybe, let's say that I will skip the stationary phase approximation for now. So now what we are doing is, let me go to the slide that I wanted to show now. So we are looking at objects like this here, and we are integrating them, but we are in the non-commutative case, and still interesting things happen. Okay, so just I wanted to mention this general case where those integrals we could think of in some way, and those cancellations are very important. And basically what happens is that along the way, so okay, let me go back to the whiteboard. What's my point? My point is sorry, Zoom just crashed. I think I had MATLAB running.
Well, at least last I heard, you said, what's my point?
Yeah. Okay, so sorry for the intermission. We lost the whiteboard. Okay, that's why maybe I shouldn't be using this Zoom whiteboard. Okay, I think my Zoom ran out of memory, but that's good. Then let me start. What's my point from scratch? So we will be deriving bounds using dx qx, which is in general an operator. So it's a matrix of dimension d. It will not be unitary because of this digression that I told you, where I was proving some condition for this to be unitary. So when we start summing unitaries, integrating unitaries, it becomes kind of a general matrix that we are just considering. And what we are doing is we are applying the norm to it, which means we are getting this multi-dimensional object into a one dimension. So this becomes a real non-negative, right? Just because of norm properties. And then the question is, what happens with those summations? And why is it okay? So actually here dx, but in general, it would be some matrix function that we consider. And why is this giving us pretty good bounds here if we integrate dx and then dx qx? And the point is that if we consider this dx qx, then this is very well approximated by x plus epsilon minus qx divided by epsilon, okay? So it's very well approximated by differences at small positions. So if I have e to ia minus e to ib, I have no idea how to approach this, but if I have e to I epsilon a, or if I have e to I minus e to I a plus epsilon b, then it's kind of clear what's happening. Those operators will be kind of closer to each other. So my point is that when we are doing this integral, we are somehow summing over, instead of comparing two faraway points and asking about the distance, we are kind of creating a path that is interpolating between them, and we are summing over this distance dk here. So dk here, and then dk here. And the point is that because we get some small epsilon into the game here to compare those complicated objects with each other, this epsilon, okay, let me write the epsilon somewhere there. This epsilon comes into play, and we have some dk of epsilon, okay? And then those dks, we can compute. We get some handle on this. And my point was that also in the case of just summing an exponential abelian sequence, it's very useful to, so if I'm summing a problem where I have some phases e phi k, so we are in the case maybe dimension equals 1, or commuting case of those matrices, only diagonal matrices considered, okay? Then it's also useful to change it into some boundary terms, and those boundary terms become important, and then some objects of this type, phi k plus 1, e2 phi k. And then we would do the triangle inequality. So if we would have the absolute value here, we would get the absolute value here and absolute value here, okay? So I can just remove those brackets. Okay, so I will link those one-dimensional materials in the description of the video later. Okay, so, and in our case, we get an integral dx from 0, 1 qx And we get just the triangular inequality here because we already prepared everything. But what I'm saying is there is a reason why this stuff works. And I keep forgetting the dx, sorry, qx here. And this derivative you can think of as doing this here, but sort of in the abelian case, that our non-abelian case. Okay, so this is a generalization. But I wanted to give you this intuition that if we have two objects and the distance between them is, I don't know, because they are kind of some matrices that I don't understand maybe, then maybe I can do this interpolation and ask a different problem. For example, using this fundamental theorem of calculus. And now the calculus of matrices, yeah? And the point is that also even in the abelian case, when you approach doing some bounds, you would consider reshaping from just the integration into, or reshaping the summation into reshaping into, so you would change the summation to a summation of the differences. If you can get this into the game, then you're comparing sort of like the local differences and expanding into the big differences, okay? And in general, it's very useful to know that basically a summation of differences like that will be a capital K minus a 0, okay? Which means there is some cancellation, and this is called telescoping. Telescoping, okay? So this I recommend to look up because this telescoping is kind of taking part in this integration here as well. That's kind of my point. That basically telescoping allows us to do this. And what happens is that those derivatives in the discrete cases, so for example, here, those derivatives are very much easier to handle. And for us, those derivatives are easier to handle. And that's why we are kind of bootstrapping the full bound. Somehow the full bound comes into play, okay? So what could happen here is you could imagine that this qx would be actually not going on the straight line. This would be the full distance. And then maybe this integral dx, whatever, would not be the full thing. But we have that the full integral is exactly the distance. So we know that this qx is actually going on the straight line. And the only question that happens is how untight this is, okay? But those bounds are actually quite tight. So for general matrices, you cannot derive better bounds. This is kind of tested, and I will say this in a moment. Okay, so that's kind of my point, that there is actually some intuition between why this stuff works, and you can try to think about the abelian case. Okay. And another thing is that it might be that this stuff is oscillating itself away, but this I'm not able to discuss much more today. Okay, this would be related to what I was trying to show. There's something in the chat. Okay, thanks, Jongrek. I think Jongrek already left. So basically, I'm posing this as kind of an open question, whether in rigorous equilibration theory, for example, like I was also working on this myself, whether we can consider those kind of non-commutative bounds for deriving equilibration of systems. I think this might still be in game. For now, we were proving equilibration using a reduction to the abelian case, and then I was using this maths literature here, for example, which is more like analytical number theory. That's more or less how it was going for this particular paper, just to give you some example how ideas can jump around. So now I'm saying I'm seeing something similar, but okay, let's get to the subject of today. Okay. So those are some slides. The slides I will link in the description later. So anyway, this is our working example, and the first thing that's so okay, share here. Sorry. Okay. So let me use black, or maybe white. So first of all, let's set the notation here. So basically we have a spin chain, and x at I means that we do the sigma x operation here, and z at some position I. So xi means that at position I we are applying this, and zj means that at position j we are applying sigma z to that spin. Okay. Maybe one thing about the notation is that it's useful to write this as the 2x2 identity times I minus 1. And one thing to figure out is really that the indices are correct. Then the sigma x matrix, then the tensor product of 2x2 identities. And then if I have D is 2 to the L, so I have L qubits. So L is the number of qubits. Then I have identity 2x2 identity 1 1 0 0, and sigma x is 0 1 1 0. Sigma z is 1 minus 1 0. Okay, so we have those three 2x2 matrices. Okay. Okay, so let's check that this is a non-commuting case. Very simple stuff. X plus 1 and then zi. If I have zj, where I should consider cases, so I is not equals to j, I plus 1 is not equals to j, then we will have that the commutator is 0. If I is equals to j, then we will have what will we have? We will have this commutator here, and basically what we will get is that the commutator will be identity tensor I minus 1, the 2x2 identity. Then I will have the sigma x matrix, sigma z matrix, tensor sigma x matrix, tensor identity to L minus I, and then minus identity again. Oops. And I will make some more space. So then the same identity, tensor I minus 1 tensor, and then here the order will be replaced, sigma x, tensor sigma x, tensor identity to L minus I. Okay, and if I erase that stuff there, I can reduce this multi-qubit commutator into the commutator of single Paulis. So there is something called associativity of the tensor product. I minus 1, and then tensor here the commutator of sigma x comma sigma z, tensor sigma x, tensor product of minus I 2/2. Okay, so this operator minus that operator is a single operator where we have here a modified operator. Here we have just multiplications and here summations. And the point is that in general, it's not so easy to do this. And it's a good exercise to study this a bit more in detail, why this appears like this. But my point here is that I found two operators here as long as if I equals to j, we have that this is non-zero because this is non-zero. Okay, Pauli operators don't commute. So that's the point of this calculation, that we found that that we are considering two blocks that are non-commuting. So let me write this here. Okay, hx operator, hz operator is non-commuting. Okay, and now we will be asking about the dynamics, and that's why that's the motivation that we want to do the dynamics. Okay, then I need to clear all drawings. And the question is whether we can do the dynamics of the full Hamiltonian as the dynamics of applying the Hamiltonians individually, and that's the point of Trotter-Suzuki. And normally, if H commutes with Hz is equals to 0, then E is the 0 operator. There's no error. There's no addition there of the wave function. There's nothing happening there. Okay, but it's non-zero. It's non-zero. Then there will be some operator E equals a non-zero. Okay, so in general, psi of t is defined as e to I t hx plus hz. Okay, and we know that this is a unitary operator. So what's going on here is that this is a unitary transformation of this. This is also a unitary operator because it's n times applying unitary operators together. So this is also in the unitary group here. And we see that we have this kind of splitting here, which is possible because of particular reasons. So I don't want to maybe say too much about this to confuse you. But basically, though, this error operator is EHX plus HZ minus E2 minus IT over NHX E2 minus IT and HZ. Okay, this would be our E operator, just a difference. It's just by definition. Okay, nothing big. But what we will show is that this error operator is small. Okay. And we were talking about this already. So in our case, what is a small operator? It means that for all psi, psi, E, psi, for example, would be a small number, yeah. For example, but in this case, E is non-Hermitian, so I should consider E dagger E psi, the maximum over psi should be small, and this is the largest singular value of this error operator that we're saying. And this means that this is the norm. So basically applied when this error operator is applied to any psi, we would like this component to be small. This should be going towards 0. Okay. That's why I was motivating all those error measures before. Okay, and that means that we have our full unitary minus un, where I define this to be un now, and this is u. Okay, so now the question is whether the operator norm of those two will be different. And for this, we will also use telescoping. So it wasn't a full discretion, but we will use telescoping in a non-abelian case. There will be a non-abelian formula, a generalization. Okay, so our bound is like this. And we will show that this is related to the commutator. I will maybe go back to BCH later. This is our bound. But now I want to show how to relate the big problem to a small problem. So this is abelian. This is non-abelian. And the source for this is Batia matrix analysis. So it's explained there how that stuff works. And we will be using everything that we used before. So I want to show that if x and y are unitary operators, I want to connect to this telescoping. So if I use this formula, then I can bound it like this, j from 0. We see what's going on in the formula. So that's what we are summing. X m minus 1 minus j, the formula tells me, then x minus y, and then y to power j. Okay, so we have again this situation, big difference. Big difference. Here we have many, and here we have a small difference. Okay, that's the situation. So there exist those beautiful formulas here that allow us to get our foot in the door. So if we take this formula, we get this, and next we use that those x, y operators are assumed to be unitary, and our operator norm, we were using this all over the place last time, is unitarily invariant. We were proving that we can have those two different operators on both sides. Okay, so removing the scribbles for clarity. Okay, which means that this upper bound is actually the summation of the same thing, m minus 1, and the complicated stuff I can forget, and this is x minus y. So I'm summing many times the same thing, so I have m x minus y. Okay, tada. So what we got is that the big difference is m times m times the small difference is, so big difference is upper bounded by m times the small difference. And that's, again, I don't know how to do it in a better way, but if I would have a straight line between two complicated objects, and I'm asking what's the norm distance here between those two objects. So that's my object B, and that's object B, object A and object B, then the distance between A and B using this norm here would be defined. Just take those two things and subtract them. okay? And the big distance is that we are creating here a bigger operator ym, and here we have a small operator, okay? So let me explain a little bit more about why I call this big and small. If I have my Hamiltonian hx and hy, hz, sorry, then they are non-commutative, okay, non-zero. But if I consider, in our case, we have e to it over n hx, and if I take this to power n, then all this stuff is commutative, so I have e to some k equals 1 until n t over n, okay, hx, because they are all commutative. So it's some kind of trick that you might want to see that this works like this. So I get e to I hx. So if I want to evolve with hx plus hhb, hz times t, then this is exactly equal, because all of this is commutative, to e to I t over n hx plus hz, and then take this to power n, okay? So in this case, I used BCH n times, saying that the products appearing here in this, they are all equal operators, so I can use BCH. Okay, I'm writing it out because I want to tell you exactly when BCH inequality happens. Even if this is the same operator, you kind of argue through BCH again. So hx commutes with itself. Okay, and if I add here hz plus hx here, this is still 0. Okay, so we use BCH here. I erase it because there's too many things otherwise. And if you use this consistently, then you have this weird sum here. But this weird sum here is just t times hx. So I erase everything and just put it there. Okay. T times hx. Okay. So this is a trivial use of BCH, and I'm erasing this because we are going to use this. We are going to use this for the summation of the Hamiltonian. So the full evolution, which is like the big, I will call it big, is n times small evolution. This is very important. Okay. So n times big is this. So this is of course obvious that the same operator commutes with itself. So now let's consider the small operator. So what is t over n hx and then t over n hz? Well, this is again non-zero. So this is non-zero. But we could ask, how big is this non-commutative part? Okay, so how big is it? Well, we could define this to be some constant c. And then what we will find, and what I'm writing here is quite important actually, we will find that this is t squared over n times our constant that we just defined c. So we get a conclusion in pink. If, well, this is a terrible color. If n goes to infinity, then Cn goes to 0. So basically what happens is that if we consider un, defined as e to I h x t over n, e to I h z t over n, then as n goes to infinity, this becomes a product of things that are almost commuting. In the limit of n goes to infinity, I mean, those are 0 objects, but they become more and more commutative, and their commutator is actually scaling stronger than n. It's n squared. Okay, both pieces here contribute 1 over n, and because of this scaling, we get something non-trivial. Okay, so it will be a good question what I mean by the scaling, but that's kind of my point. So this is actually a good point and important to slow down. I don't have much space here, but let's say Trotter-Suzuki decomposition involves almost and here we wanted no almost commuting objects. Okay, so that's quite important. And let me tell you one more thing. Semiclassical limit of spin. So if I have a helium atom and I go on n to infinity shell, then basically the orbital angular momentum L of the electron on the orbit actually gets more and more dequantized. It becomes more and more a semiclassical angular momentum, and it's because there's always more, there's probably something like 2L plus 1 levels or something like this. And so if I would consider different atoms with a very high orbital angular momentum and they are scattering with each other and so on, this quantized, those quantized angular momentum level, they start behaving semi-classically. So SL alpha and then S alpha, let's do maybe beta alpha commutator, it kind of goes to 0. That's the idea. That's how people argue, how do you get the continuous spectrum of angular momentum in classical mechanics. That's one idea. So we have this here, and our kind of transformation is doing something similar, that basically there is some new scaling of the strength of this non-commutativity. Hz, and this is smaller than t squared n squared, the commutator hx hz. Okay, so this is this kind of transformation. That's more or less physically what it happens, and what we have here is that if we do bounds, then we forget this stuff, and we can use this formula here to transition from one to another. Okay, so we are almost there. I'm only trying to explain all the things that are actually coming in, why this works, and I want to show also one more thing before we finish the bounds. I mean, just the bound itself is quite easy, but let's consider this problem that I have u minus un, and let me show it this way, that basically here I have e to it hx plus hb, hz. And let me insert here something silly. T n minus 1 n hx plus hz times e to I. And here I have still t here, t over n hx e to I t over n hz. And I'm inserting a 0 here, so I need to rewrite this, sorry. But once you see this, this is a very good exercise. So this is t hx plus hz, close the bracket here, and then here plus un. Okay, un would be just taking, oh, wait. IT over n hx it over n hz, and here I have plus no minus, I have minus, and then here it over n hx it over n hz 2 power n. So what I can do is I can make this into an inequality by inserting the triangle inequality here, and the plus stays. Okay, so now what I can use is it's norm invariance. So basically here I can rewrite this using this trivial BCH. So I will only do this favor to you that I will write this here like this. Hz, and then I will have e to it over n. You see that if I sum it here, it will fit. And here I will have the summation x hz plus hz. And here I will have this minus it n hx and split the product. That's the key thing. That's why we are writing so much. hx hz. Close it here, close bracket. And then here we have something similar, only that this cancels, okay? So we are starting to drop, whoops. We are starting to drop some products. And we have always less strength of that operator there. So many scribbles there. Scribble, go, okay. And I wanted to remove this, okay, throw. T hx plus hz like this minus e it over nhx e to it over nhz, and the power is now lowered because I just pull out again the factor. This is a common factor here. We can pull it out and use unitary invariance. We can replace this by identity, okay? And that's an inductive way of doing this kind of telescoping. And again, the feature is you have 2 points and you kind of try to bring them closer together. That's what we are doing here. And this is a variant of telescoping. It's just now I perform this in an inductive way. So this goes to, what did I do? So this object here will go away. And what we have here is that this is already the small one. This is small. And this is big, but infinitesimally smaller. So, and what happens is that eventually we sum over all of those m's. M here is infinitely big or tending towards infinity, right? So it will become always larger, okay? So if we keep repeating this, we will get this again, okay? So let me do one more step. This is unitary invariance. This goes away, this goes away. We have the norm here. And then I could repeat this again. So I will get this twice and I will get -2 and here -2. Then if I do it again, I will get 3 and I will get 3 here. This is how induction works on paper. 4, 4, 4. And at some point I will get n here, I will get n here, and I will get n here, okay? So what happens if I get n there? So I just did on the whiteboard the case if I do it n times. If I do it n times and n times here, this becomes 0, this becomes 0, okay? So the whole thing becomes this also goes away. This becomes a huge way of writing identity because any operator a to 0 is identity. And then minus, a huge operator, which is identity. So this becomes 0. So this is a huge 0. But we have here this n, okay? So this is a different way of deriving the big operator minus the small operator by inserting this identity that I'm now erasing, okay? So erasing. Okay, this maybe will look terrible as an end effect, but this is smaller or equal, this n times this small. So we again have the big is bounded. Here it's bounded by n times small. This is the small stuff, okay? That's the scribbles. And the way we do it is we try to see in the big one something that still looks big, but looks a little bit like this one, okay? And the continuous way of doing this, continuous version of this, sorry if the scribbles are quite terrible. The continuous way of doing this is this slide, okay? So now we want to say that I want to interpolate between the small and big, and we will be only bounding the small part. So now let's say this is e to it over n hx. This will be that, and this will be e to it over n hz. Okay. And what we will get is that this is bounded by that. So if I want to do this without the t over n, I can do n times this commutator here. That's how those bounds are working, okay? So now I will go through the whole thing because we started seeing how telescoping comes in here or there. So the point is that if we are using the telescoping trick, then I showed you two different ways of applying this. But if I just apply the formula, then I have this here on the slide, okay? Then this is our operator x, and this is our operator y, okay? And is that how? No. This is our operator y, and our operator x is e to it over n hx plus hz. Okay, just redoing what I was showing already. So this is x. So this is x to power n, and this will be y to power n if we include this here. Okay. So just using the formula here with m equals to n, we have our x operator on both sides. This is actually wrong on this slide. I need to correct this. So the correct way would be hx, there would be some sort of power n, and here would be plus hx to power n minus j or something like this. So this is actually incorrect. But either way, this is unitary. So this goes to identity, this goes to identity, as I was saying. So I was explaining this a little bit better before. So the slide has something wrong here. And so we get basically n times the bound on this. Okay, so we can forget this. And so that's the meaning of this identity here. The proof of this identity is not so important. We can do the same thing with the brute force telescoping that I was explaining, this inductive telescoping. Okay, so going back to what we wanted to show. If we split this stuff, I will have n times the small commutator of those objects here. Okay. And n times this squared basically removes one power, so that's why this power vanishes here. Normally, t squared n squared. But if we connect big and small, then we have n times this small stuff. That's the rule. So that's why it drops here. Okay, that's one comment. So we basically derived this already, but we didn't derive that e to I t over n hx plus hz minus e I t over n hx e to I t over n hc is smaller or equal than Tn squared commutator hx hz. Okay, for now we know that this is n times this, so we don't have this yet, but we have this bound. So the error is bounded by n times small. Okay, that's what we did so far. And maybe at some point I explained the BCH formula, how it can go into play and why it doesn't suffice, but I'm skipping this all the time today. This is how to do the small bound. And now I was showing that we have n this, we have n this. So now the question is how to bound the norm of this. Okay, maybe I also stop drawing with that. And I will go back to the Zoom annotations. Okay, so how to bound this? And when we have this, we are already done, and I already almost tried to talk about convergence rates and pointwise convergence and so on. So we can discuss this in a moment. But once we have this bound, we are done with Trotter-Suzuki decomposition. Okay. So let's try to see. And I have the slides for this because here we can speed up. We did very carefully the bound e to IA minus e to IB. But if we have a bound e to IB plus A here, then we need a different ansatz. Okay, so now we have a new ansatz. This is this ansatz. So what do we see? At 0, it's interpolating to the split product, and at 1, it's interpolating to the joint product. Okay, so we're almost done. Now we would need to compute the derivative. Maybe if we have time, I should show it. But if not, then basically we can do the same stuff. Okay, there should be an inequality at some slides that maybe are not very correct right now. Okay, so we can do this calculation. Let me check the time. So, okay, I'm going over time, I think, slowly. Maybe 5 more minutes or something. So basically, using the this transformation here, we already have the proof structure, yeah? So I have, let's see how everything that I have on the slide comes into play. I have those two objects, which means that Q0, actually Q1 minus Q0, this is equal to Q0 minus Q1, because this differs by multiplying with a scalar, and that's one of the axioms that the scalar goes out in absolute value. So this is times absolute value of -1, okay? So that's why the order doesn't matter. But the order will matter for me for the integral. So I will have the integral dx outside dx qx. Okay. And if I want to make it smaller or equal, I will integrate the norm of dx qx. Okay. And because I will be taking the norm, this stuff doesn't matter. It goes away in the norm. Okay, here it doesn't go away, so I'm keeping track of it. But there it goes away. And one thing that becomes a little bit more difficult is that, okay, so the norm of this is this goes away, this goes inside, and the norm goes here. And what do we see? B cancels with B. So this is already going away. So, so if I want to get this bound, I will be now doing this more carefully. I have minus A plus AB. And I need to explain a little bit about AB because this is not something we were needing last time. A minus AB is something where in the calculation here, you kind of see that to be able to pull out those unitaries jointly to use this unitary invariance, we need to define this AB, which is the operator A evolved to time 1 minus x under this operator B. And you see I have here a minus, this plays the role of the time and so on, okay? And one thing that also applies to functions is that you have this Lagrange form of the Taylor expansion. So fx is equals to fx0 plus the derivative evaluated at some point xi. And I will have to have here x minus xi, I think. No. There will be the polynomial somewhere here. No, I don't remember whether I have to have this to power n for n power. How did it go? No, maybe I just can evaluate this at the point f0 and xi. No. Times xi, I think. Is this true? So basically the idea is that if this is considered a function of x, then I can evaluate at x equals 0, or I'm actually doing this around x equals to 1, then this is identity, this is identity. So my f of x0 is equals to a. And then I need to compute the derivative of this object and evaluate that derivative at some Lagrange point sigma xi x. That's what I was trying to do here. And I might be missing here some xi x to be added here. But the point would be that this xi x at some point goes away. So maybe I just found a second problem on my slide here. Okay. I would need to check the Lagrange form in a moment. Okay, so long story short, this is supposed to look at fx plus is equals to fx of 0 plus f prime of some point xi times possibly some xi x minus xi or something like this. Okay, that's the Lagrange form of the Taylor expansion applied to matrices. Well, if you get this stuff right, then A cancels with A, B already canceled with B, so A will cancel with part of it. And whether there's xi x or not, let's put the xi x if it's needed, or maybe it's not needed there. Then the whole bound, until we get here into a bound, we will get that this is the norm of e to I xi xb, which is unitary replaced by identity, a b, and here we might have a xi x, and here we might have a dx, okay? But this xi x is always smaller or equal than dxx, and then a b norm. This is x independent, okay? I remove the box. So this is from 0 to 1, which means that actually this becomes 1/2 here. It gives us a factor of 1/2. If I skip this integration, if I bound it by 1, so xi x is smaller or equals to 1, I don't need to expand around x, then it becomes even simpler because dx from 0 to 1 is equals to 1. So if I skip this sigma x, xi x, then I get this bound. If I don't skip, then I have actually this constant 1/2, and that's what I meant, that I'm always forgetting those constants, whether they are there or not. Okay, so this is Lagrange Taylor residue or error bound or something like this. Okay, so what we get here is a bound on the small part. Small is the small part is bounded by non-commutativity. It's our measure of how non-commutative those operators are, and big is n times that. Okay, and the last thing is that I was explicitly writing out those painful factors e to I t over n h x, e to I t over n h z. Okay, so our a is equals to t over n times hx. Okay, so so basically if we do this, then we finish with t over n squared and then the commutator. Almost done. Long session. Norm hx hz. Okay, this is this commutator. That's why we get t squared, because t over n comes in here and for b also comes in here, so we have tn squared. The big is n times the small bound, but we just showed that the small bound, I remove all the scribbles, is bounded by the commutator, depending on how careful you are about the Lagrange form, there should be some sigma psi x here to make it into an operator inequality. If we work on inequalities, then it will be similar. Okay, so okay, so we started with the errors. We showed that we have this error operator giving us some perpendicular portion of this, some perpendicular superposition of error wave functions. We were bounding this in this way, so I was doing this n over n, adding here and taking powers to n. And then we had the induction, and we got this bound here. So those slides really give the full bound. And one aspect is telescoping. And once you have telescoping, nonlinear interpolation, and the nonlinear interpolation is using precisely what I was saying to connect to derivatives, which will appear, I think, in the box, the derivative appeared in the box, okay? And those derivatives, they have actually meaning, but we are using this in the non-commutative case, so it's harder to give some intuition. But the idea is that we have two objects far away. They have some distance between them. So this would be actually the distance between Q0 and Q1, where Q0 is splitted and Q1 is non-splitted. So how much are they different? That's the point. And then we take the norm, put the norm inside and get an inequality in terms of the commutator. Okay, so what we get is that that basically the splitted evolution here differs from the small evolution here by this factor. And then maybe next week I will explain more about how this is pointwise convergence, because there's a scaling in T. So if this T is coming in here, we need to always increase N and so on. So maybe this I will do next week. But the fundamental bound here is saying that the difference between doing this and splitting the evolutions and applying them in small portions is that the error will be at most a measure of how non-commutative those Hamiltonians here are. Okay, too many errors here, but okay. Okay, so